We talked about transducers as the basic elements, as sensing elements, which will convert energy from some form to electrical energy, and it can do vice versa as well. So we said that when we are dealing with semiconductors, it's easy to understand the case of optical transducers because we have already talked about the carrier mechanisms inside a semiconductor. And now it's easy to see that if I'm going to incident some light on the semiconductor, then I can generate carriers. And we said that that can lead to something called the solar cell, where you have light energy and you get electrical output. The converse of that is you can give electrical input and then get light output. That's what a light emitting diode does. So we talked about the fact that you have the conduction band and valence band segregated by some band gap, Eg, and when you emit light of a certain energy which is greater than the band gap, then you can excite carriers directly from the valence band to the conduction band. Okay, and in this way you are generating charge carriers. If it's a simple piece of semiconductor, that means there is no n-type, p-type doping. There could be n-type or p-type doping, but there is no diode. So it's just a bar of semiconductor. Then as you shine light on it, the number of carriers increases and the resistance goes down. So this is a variable resistor that looks like this. And as you shine light, the resistance changes. On the other hand, if you want to make it a diode, that means you get a photodiode, whose symbol looks like this. Then you can shine light, and the depletion region the carriers generated in the depletion region will create an imbalance because the positive carriers will go to one side and the negative carriers will go to the other side. And thus you can generate a potential at the ends of the diode. And that way the diode becomes an active device. So normally in the past we studied that the diode is a passive device, it cannot amplify and all of that. But here it's actually an active device and it can generate energy. If you want to use it as a photo detector, you can potentially add some reverse bias to the diode and ensure that the collection of carriers is enhanced and the rate at which it happens is also faster. So you can get a better response time as well as you can get more current. So this is what we discussed with respect to the photo detectors and photoresistors. Also, the opposite of it is the LED, where you can have a diode with the appropriate kind of materials and the band gap. So it need not be silicon, it can be different kinds of materials. And what you would have is, if it's an LED, I'll just write it briefly here. So it's a regular PN junction diode. And now what we say is that if I forward bias this diode, then you expect that current will flow, that holes will get injected on one side and electrons will get injected in the forward bias. This is regular behavior of a diode. Now what happens when you have a photodiode, then you have the special case that these electrons and holes can recombine, and when they recombine they'll shine light. So those electrons and holes will recombine and give out light. That's what is a light emitting diode. So it's the exact opposite process of the photodetector, where light is shining into the diode over here and it is generating carriers. Here it's the opposite. You are applying energy, so you are supplying electrical energy, you are forward biasing the diode. As a consequence, the majority holes and majority electrons of the opposite sides, they recombine with each other as they traverse the depletion region. And when they recombine with each other, they shine light. Okay. So this is LED. Just as we talked about the diode, you can also have a transistor. And in the case of a photo transistor, what will happen is that I have a BJT. So this is the regular symbol of a BJT, and this is a NPN BJT because you can see that the arrow is on the emitter side going out. So it's an NPN BJT and there is light shining on it. So this is the symbol of the phototransistor. And the phototransistor can be thought of as having a photodiode which is connected between the base and the collector over here. Okay. So normally what will happen is if you shine light, then some carriers are generated. And when the carriers are generated, then that adds as a base current. Okay. So the base current increases. Because the base current increases, then the collector current also increases. So the current going from the collector side is like the base current times 1 plus beta. Okay. So this is also a mechanism of a photo conversion of, a device that does photo conversion. But what's different between this and the diode is that in the case of the diode, which was the portion over here, in the case of the diode, what we saw was that if I shine some light on the diode, then I have some carriers which are generated. In this case, we have taken it one step further. I've shown some light on the diode, carriers are generated, and the current has got amplified now. So in the case of a photodiode, I had a current which is equal to ICB. In the case of a phototransistor, that current is now amplified by a term 1 plus beta. So in addition to a diode, you have amplification. So these are the basic uses of the semiconductors when you're using them as optical transducers. So we talked about 3 kinds of optical transducers. The first is the photoresistor, right? So photoresistor means there is no different P and N region. It is just one uniform piece of semiconductor. So one uniform piece of semiconductor which is getting affected by light, and this is the symbol of that. So this is a photoresistor. In the second case, we said that we are now taking that piece of semiconductor and doping it on the 2 sides to make a PN junction diode. So that gave us a photodiode. So this is the second type of device. A photoresistor is a device in which you increase the number of carriers, but it only changes the resistance of the device. It does not do anything else. In a photodiode, you're increasing the number of carriers and you're separating the carriers. You're pushing them on either side, and therefore you have created a directed current flow. So this is behaving as a active device where you're able to cause current to flow, and that's like your solar cell or a photodetector. So all of these are your photodiodes. And the opposite of that is the LED, which is also a photodiode in some sense, but we don't call it a photodiode. It's the reverse process where you apply a positive bias, and in the process you generate light coming out of it. And finally, we talked about the phototransistor, which is a 3-terminal device where you have the photodiode plus amplification, so you can get more light out of it. Now, normally this phototransistor is, you might wonder that this is the best device because after all you're getting the best amplification over here, but it's not necessary because sometimes this kind of device, a phototransistor, may not have good response time because it takes a certain amount of time for the amplification process to get restored. Supposing the light is on and then the light is off. So we are just talking about one event where light is shining on the material, but supposing this is a changing light, supposing it's an optical device where the signal is being given as light. So you can have high frequency signals, and the rate of response of the transistor is not as good as the rate of response of a diode. After diode is only one junction, so it has less work to do. A transistor has 2 junctions, so it's a little more complicated. So it takes more time to respond. So these are the different comparisons of the optical devices. In the last, I just picked up one picture that was there online. You can see when you're doing your BTech projects or something like that, how exactly you have to set up this system. So here you have a light source, which is your transmitter, and you have a light receiver, which could be your photoresistor. Okay. And then you have the alarm system over here. So when the light beam is shining, this is the example we discussed yesterday. When there is a light beam which is shining, then the LDR, the photoresistor, is at a certain state. And if somebody breaks the light beam, then the state of the LDR changes. And due to that, whatever current is flowing in the circuit changes, and then it can trigger an alarm. So very simple case. Here is a little more complicated thing. We talked about just a photoresistor, but supposing you want to do it with a phototransistor, that means you have this BJT, and you can see that this particular BJT is having the base biasing so that you have the resistor divider network. And this is again, current is flowing out of the emitter over here. So when you have the light shining on the diode, then on this resistor, then its resistance is very low and there is a base current flowing. If the light supply is broken, then this resistance becomes very large. And because this resistance becomes large, then the VBE becomes very small, right? So the transistor will go into cutoff. So originally the transistor may be in the active mode or saturation mode. And once the light source is cut off, then this resistance becomes very large because of this diode, because of this resistor over here. And therefore this becomes open circuit. And if this is open circuit, then the entire voltage may drop across here and VB will become small value and the transistor may go and cut off. But there can be different mechanisms depending on how you connect the battery supply and all that. But that's the basic logic here. So how do you ensure that there is a response to an incident light? Okay? And this is where you have to worry about the appropriate biasing. And you can see that if I use a transistor, then I can get an amplification of the signal. So even for a small change, I can detect a large signal in the output, and that amplified output will then be used for a further circuit to trigger something. This is much like what we saw in the very beginning in the top when I drew that system here. So the is your light source. Then you have a sensing element, which is your light dependent resistor. The signal conditioning element, which we said is like the amplifier. And then it passes it on to a signal processing unit. So that's what is happening in this very last step. You have the input, which is the light source. Then you have the LDR, which is the sensing element. Then you have the amplification element, which is the amplifier. And then that is taking it forward to some signal processing unit, which will then decide what has to be done. So this is the case with photo transistors. Yesterday there was a question that one student asked, which I later thought, and I was not clear what exactly the question was. There was something about, I think, the flow of carriers, because he said something about if you have positive potential on one side and then you have the battery also connected and the charge carriers flow into the battery. So basically, if you apply a reverse bias across a PN junction diode, then what we said is that the pulls the majority carriers away from either side. So the holes go into the battery and the electrons go into the battery. So this is a normal process of current flow. So when you shine light, then you're creating holes and the holes are getting pushed to the P side. And from the P side, they're going back into the negative terminal. So far there is no difference from the original reverse bias diode. Nothing has changed. Only more current is flowing. Originally, there was just some reverse saturation current, which we called a dark current. And now if there is light shining on this material, then that current increases. So there is a greater reverse current and it still satisfies the battery. So there was no issue with that. The question was that how well does the diode respond to a given incident light? So if I have like these characteristics over here, sensitivity, for example, that if I have light flowing into the diode, light shining on the diode, then how much will the resistance change? So how responsive is it to some applied input? So for a given amount of input illumination, which is in candelas, how much will the device change? So that is the responsibility. And response is how quickly it will change. What is the value beta for a photo transistor? It's same as a regular transistor. It depends on how you design it, what kind of material you use and all of that. So beta can be 100, 200, 500, whatever. So photo transistor can be just thought of a regular transistor. There is nothing special about it. It's just a regular transistor. And then you can think that it has a photodiode which is connected at the base side. So that whenever you apply a light source, so whenever there's a light source, then there's a current flowing, right? And this current flows and then you have a base current flowing into the system. If the light source is cut off, then may not have any current flowing in the system and therefore the base current reduces. So as the light flows, as the light is incident on this diode, more current flows. And as the base current increases, the collector current increases. Because collector current is base current into 1 plus beta, or this is like ICE, should be beta IB. Some notation they have used here, I'm not sure what. But basically is that you have some base current which is amplified by beta times and you get a collector current. It's nothing but a photodiode which is amplified using a transistor. Now modern photo transistors may have novel features, like people use things like heterojunctions. So that normally we have discussed a NPN transistor which is built of silicon or germanium or some material like that. But what people do is they develop NPN transistors where the emitter is using one material, the base is using a different material, and collector is using a different material. So these are all advanced techniques where you use different materials for each part of the transistor. Earlier, from our perspective, there was only difference in doping and difference in dimensions. Now it's like a difference in material also. So these are all various things that people do, and there are some faculty in ITMND who are just working on this. So it's a deep topic. But bottom line is it's just a transistor which is amplifying the light signal of a light diode. So in today's class, then what I'll do is I'll just briefly talk about the other set of transducers, which are thermal. And this will be a very general discussion. There is not much theory or detail to get into. Just a overview of how thermal transducers are working. So just like we said that light is one source of generating energy, heat is also a source of generating carriers. Light is an energy source which generates carriers. Heat is also an energy source which generates carriers. Normally what happens is you can end up with two kinds of materials. So the response to temperature is a little more complicated. Sometimes you can have materials like a semiconductor material, which does not have much carriers in it. So if you don't have much carriers, then what happens is as you supply heat to the system, then you generate carriers. So what happens is then you get electrons and then you get holes. So as you apply heat to the system, you can generate more number of carriers. And as a consequence, you can increase the conductivity of the material. There are also other materials like metals, which have a huge, I'm getting a lot of beeping sound. So what happens is in the case of a metal, where there are already a lot of carriers, there are already huge number of electrons, then by increasing the temperature, the slight increase in number of electrons is not too much. But on the other hand, the existing electrons, which already have contributed to high conductivity, they experience carrier collision, and due to experiencing carrier collision, the resistance increases. So you see, there are two kinds of materials. Those which have, this is a very simplistic way of saying things. If you go into the physics, there are lots of complications. But those which start with small number of carriers and large number of carriers. So when you have small number of carriers, the effect of temperature is to generate more carriers. And as you generate more carriers, the resistance goes down. So this is a material in which you can see the decrease in resistance. Whereas on the other hand, you can have a material which already started with large number of carriers, and therefore it doesn't help too much. That as I heat it, it's not like I'm generating too many more carriers. Supposing I already have 10,000 carriers and I'm generating extra 100 carriers, that does not help too much. On the other hand, the existing 10,000 carriers start experiencing collisions due to temperature, then the resistance actually increases. So in some cases, it can help the resistance. In some cases, it can worsen the resistance. Okay, so that's the way temperature behaves in a kind of a contra-intuitive way, depending on different material types. So if you look at the case of metals, metals usually have high number of carriers, right? We know metals are conductive by nature, all most popular metals. Copper has very high conductivity. It's one of the most conductive metals, silver and so forth. So if you were to take a curve of temperature versus resistance, you actually find in metals that the resistance increases with temperature because there are already a huge number of carriers, and therefore the temperature keeps increasing. Now, on the other hand, you can have some materials like ceramics or semiconductors where if you increase the temperature, then you're actually reducing the resistance of the material. So these are different kinds of materials. Okay. So these are called RTD devices, resistance thermal detectors. These are usually made of pure metals, RTD. I think this is what it stands for, resistance thermal detectors. In quantum-based devices, RTD also stands for resonant tunneling diode. So if you Google search, don't get confused. So resonant tunneling diode is a completely different thing. This is a resistance thermal detector. And here what happens is you can see that some of these materials behave in a very linear fashion, like platinum. The temperature resistance increases linearly with temperature. With copper, it starts off with some linear regime and then it changes and goes to a quadratic curve. And say nickel, initially it changes, increases a lot, and then it becomes linear. So different materials may be used for different ranges of operation. Okay. On the right side, you can see R1 by R naught, right? That means it's a normalized resistance. And you can see that it starts from 1. So R naught is probably the case where it is equal to 1. That means at 0 Celsius. So the resistance at 0 Celsius is R naught. So then these are actually taken with respect to the resistance at 0 Celsius. There is no absolute number. This is not in ohms, right? This is a normalized unit. So for every material, you are considering what is its resistance at 0 Celsius. And then as you increase the temperature, you're seeing how much does the resistance change compared to its 0 Celsius value. So that's what you're plotting. And this is called normalization. Okay. That means there are no units. Now, similarly, we said that there are other kinds of materials which are like thermistors, called a thermistor, where you can see that the resistance actually reduces. In this case, see the y-axis resistance is in ohms. This is not normalized. So this is real resistance values. So this resistance reduces as temperature increases. And for the case of RTD, which is shown here, you can see that the resistance increases as the temperature increases. Okay. And the RTD, in this case, whichever material they used is linear. And the thermistor is clearly strongly non-linear in its behavior. So these can be used for different functionalities.
So, sir, in RTD we use only metals.
Most RTDs have only metals. Sometimes it can even have an alloy, but usually the RTDs that I am familiar with, that I have seen, they're usually single metal RTDs. But now there will be like different materials and all. There's nothing, there is no gospel over here that it has to be only this. These are all things which started off, which were developed, say, about 50 or 100 years ago. And now, you know, as things have changed with the modern nano electronics, people have come up with novel composites, mixtures, because there are new ways of fabrication, new ways of melding metals and materials. So as the technology improves, a lot of these definitions will change. This is why what I want to be clear here is all of these are fundamental understanding of how these devices work. But don't expect that when you go to the job industry, you'll find exactly the same thing as you're learning in class. Because depending on the different applications and requirements, you'll find a lot of variations. So just keep that in mind. That's why I'm a little hesitant about sometimes going into very specifics of certain answers, because the more specific you go, it is very situation dependent. So the principles we are discussing here are very general. That you have those RTDs, which typically are usually metals. Now, tomorrow, if somebody comes up with an RTD which has a non-metallic, substance, what can we do? So usually it has been metals, and they prefer to have it pure metals. These are especially used at very low temperature experiments or where you want very precise measurements. Because when you have a pure metal, then it is not contaminated by any other material and the behavior is very predictable. Because there are many other things to worry, like whether the response is linear, whether the accuracy is there, whether it's precise. That means that there should not be variations as a function of time. So is it going to be precise? So all of these are obtained by getting pure metals. And usually when you use pure metals, the systems are also very expensive, because it's a complicated process to get something of very high purity. Thermistors will be much cheaper. So thermistors will be much cheaper because they have these kind of nonlinear characteristics and they don't have to cater to such high precision. These are some differences, it's just good general knowledge, but beyond that, you don't have to worry about it right now. So here is the symbol of a thermistor, and this is also another symbol of a thermistor. And if you were to search online, you will find that depending on the different nations, whether in US, Europe, or different locations, different Australia, sometimes there are different notations and all of that. So this is also just as information for you to be aware that there are these things out here. These are also called as positive thermal coefficients. And can everyone mute themselves, please?
Sir, what's the difference between thermistor and RTD then?
Here, this is what it's showing. So usually you see that the thermistor is something which has a negative thermal coefficient. So let's call those as NTC and PTC. So thermistor has a negative thermal coefficient or negative temperature coefficient, and RTD has positive temperature coefficient. So in one case, you can see the resistance increases with temperature. In one case, the resistance reduces with temperature. So you can have, different uses. Just like this, I picked one for thermistor also. So you can see that if you see on the right side over here, it's like a water level detecting system. Supposing you are going to work on your design practicum in your next semester or the next year, you have another course where you have to build such systems using Arduinos and sensors and all that. And here is an example of how, if I want to build a water automatic level detection system, then you can have a thermistor. And what will happen is when the water level goes up and it touches the thermistor, then the water will cool it. And because of that, its resistance will change. And when the resistance changes, then some current can flow and then it can give an alarm. Okay. Otherwise, normally the thermistor has high resistance at low temperature. Yeah, so the thermistor has high resistance at low temperature and it has a low resistance at high temperature. So you can think about how to use these devices. So if you want that, there should be
Explain it again.
Sorry?
Sir, please explain again how thermistor is used in alarm.
Very straightforward. All we are saying is that I want to detect the water level. Water level should not exceed some point. Supposing this is my tank and this is my water level limit. After this, it will start overflowing. So I'm going to keep a thermistor. And when the water level increases, supposing there is a pipe or something which is pouring water over here, and the water level is going on increasing. When the water level crosses this limit, then the thermistor, once it gets surrounded by water, then what will happen is its resistance will change. And because its resistance changes, then the amount of current flowing will change. And that will trigger an alarm, or it can trigger a circuit, an actuator, say an Arduino thing. Board is connected, and once the Arduino gets the signal, it will have a GPIO pin which will send a signal to a valve over here, and the valve can close the tap. So these are all ways in which you can use this. Very straightforward, there's nothing complicated. It just looks like there are lots of blocks and all that. But the reason you have something like this is what I talked about is very simplistic. I'm just putting a thermistor and its resistance changes. But then just like we talked about a photo detector, right? We talked about dark current and things like that. So supposing there is a dark current associated, so-called dark current associated with a thermistor, then that current can also trigger some alarm. So therefore you need some special current level sensing units. You may need to put something to ensure that noise is cancelled. So there will be some circuitry that you have to put here. These are like your signal conditioning circuits or signal processing circuits. This is just your sensing element, right? Same block like we discussed earlier. You have a sensing element which gives an output, then you have your signal conditioning, signal processing, and then some actuation happens. So here is an example of a switching type of positive temperature coefficient device. So normally you see that the temperature coefficients are, the resistance are increasing in a very gradual fashion. So this is all gradual increase in resistance, right? As an increase in temperature. Whereas this is a material where you can see that probably it is not made of a single material. This might be a composite of multiple materials. So at some initial temperature, for low temperature, it almost shows the resistance reducing, increasing, and then suddenly it undergoes a transition. Usually when you see this kind of sudden transition in materials, usually you know that this is some kind of a phase change. The material change from one phase to another phase. If you do some material science course, you'll read this. So these kind of things result in such abrupt transitions. So that's what this is. So this can be like a switch, right? Just like we talked about the common emitter amplifier. We said that if I have the common emitter amplifier characteristics, the V out and V in, then this linear regime is the amplifier. And then we said that the switching has two levels, either high or low. So this can be thought of a switch. This is a low level and this is a high level. So if my temperature changes, so as long as I'm at some reasonable level of temperature, which is okay for me, the device is on. And then if it exceeds some value, then it will turn off. So this can be like some overload protection, right? Or I can have this in a circuit that looks like this, that I have some electrical appliance on my 3-pin plug, and there is the appliance over here, like a mixie or something. And in between, I'll have a thermistor over here. So what will happen is that supposing we talk about overload protection. So supposing there is large current or fluctuation and large current flows, then the current will create a heat proportional to I square R, the resistance of the thermistor times the square of the current. So when something like that happens, it will create a lot of heat, I square R. So when you exceed a certain temperature, then suddenly that threshold value will increase and the current will stop. It will become like a fuse or something like that. So these are all various applications of thermistor. Okay. Trying to think, yeah, I think that's all there is to this. I mean, it's very straightforward. It's just like we said that light affects the resistivity of a material. Temperature also affects the resistivity. And unlike the case of light, here you saw two cases. Depending on the nature of the original material, if it's something which has small number of carriers, like a semiconductor or some ceramic, then you can see that the resistance reduces as temperature increases. On the other hand, if it's a metallic system or a system which has a large number of carriers already to start with, then you're not helping generate too many carriers, but you may affect the existing carriers. So the resistance actually increases with temperature. So that's your positive temperature coefficient and negative temperature coefficient. There is also something known as the Seebeck effect. I think you may have studied about at some point earlier in life. The basic idea is that if you have two dissimilar metals, this is the important point. If you have two dissimilar metals which are welded together at one end, then what will happen is that if one end of those metals is kept at some temperature T1 and the other end is kept at some temperature T2, then there will actually be a flow of current in the system. Okay, it will go from one junction to another junction. And this actually arises from the band structure. Just like I talked about the conduction band, valence band, and Fermi level and all that. Actually, it's the same physics that creates this motion of carriers. So if I have two materials having two different conduction band, valence band, and Fermi levels, and they're connected in this way, then what happens is, due to the non-uniform distribution of carriers, when you have the temperature applied at one end, say one temperature is hot, and one material has lots of electrons and one material has less number of electrons. Now, normally what happens is when you give heat as an input, then the electron gains energy and it starts moving. So the electron will move from some hot end to a cold end. Since one of them has more number of electrons, so it will result in an asymmetry. So more electrons go from one side than from the other side. So since more electrons go from one side, then you end up having a potential difference. And to match that potential difference, then the balance of electrons again flow back. So some procedure like that happens. Okay, we are not going into the details of it, but I just want to let you know that normally we always, it was like a mystery for us. We just take two dissimilar metals and you weld it and put one temperature at one end and other temperature other, and somehow magically current flows. So this is all actually coming from the electron theory of these solids, about how the distribution of charge carriers and the Fermi levels or potentials inside the metal. So this is called Seebeck effect, and then you can have the regular definition for it, that supposing I have these two metals which are welded at one end, and at the other end I'm inserting a voltmeter. Then I can measure some voltage, Seebeck voltage, and that is given by this equation, which depends on temperature. That means there is a temperature difference between one end and the other end. and correspondingly it results in a voltage difference across the two ends, and that is related by some Seebeck coefficient. So we don't need to, I think, get into all this. Just to let you know. In fact, when you think about the people who started these experiments, right now we talk in terms of theory and try to explain how things work. But the person who discovered this for the first time, he did not understand anything about electron theory of solids and all that. They had just discovered this phenomenon that you have two different metals and you connect it and you have this voltage. So this is how normally you start with your initial level models. You know that there is you go to the lab and you measure. You put one end in ice and you put one end in a bucket of water, and then you put a heater below it and you start heating the water. And you keep a thermometer. So you keep measuring how much is the temperature difference. As the temperature is changing, how much is the voltage developed? And then you plot a curve, voltage versus temperature. And the slope of that curve becomes your alpha. So this is how people actually build models. Okay. So I'll just show this quick figure and then I'll take some questions. Here, basically what you can see is that I have one end which is at temperature 1, which is the cold end. Let me make this a little larger. So there is one metal A and one metal B, and I have one end at T1 and one end at T2. And since this is a short circuit, that means it's just two welded ends which are connected at two different temperatures. Then there is a flow of current going in a certain direction. Okay. So this is called the Seebeck effect. And in between, if you were to insert a voltmeter, then what will happen is, because the current cannot flow, you have broken the path of current. So current flows on one side and then it comes here and accumulates on one end of the voltmeter. So because of that, a potential difference is created and you're measuring that and calling it the Seebeck voltage. If there is no voltmeter here, then current will just keep flowing. Okay. And there is an interesting thing. What this current is doing is it's actually carrying heat. So the current which is going from the hot end to the cold end is carrying heat and it's going and depositing it at the cold end. Similarly, the current at the cold end is basically being driven by a potential difference, because the current which was first created by the hot carriers, so because of the heat some carriers are created, they are going to the other end and depositing energy. So the temperature part is gone, but now because there's accumulation of carriers, there's an electrostatic potential created. So that again drives the carriers back. So that's how this loop happens. So this is why it's a transducer. There is a interdependence of electrostatic energy and thermal energy. So thermal energy drives it in one direction, electrostatic energy drives it in another direction. So that's how this system keeps going. So if you break the flow of current and you put a voltmeter, then you can measure what is that electrostatic potential which is created, and that's called the Seebeck voltage. And you can go one step further. Now that I know that there is a potential created in this system, I can remove the voltmeter and put a battery so that I'm forcing the current to go in the opposite direction, right? So earlier current was going from the hot end to the cold end in metal A. Now I'm forcing the current to go in the opposite direction. And see, there is something interesting here. Now this is not kept at T1 and T2. This is now kept at room temperature. But through the process of pushing current like this, you are creating a reverse effect called the Peltier effect. That means you are now making this go to temperature T1 and making this go to temperature T2. So this is the reverse of the Seebeck effect. So the Seebeck effect is taking thermal energy and converting it to electrical energy. So due to hot end and cold end, you are having current flow, conversion of thermal energy to electrical energy. The Peltier effect is the opposite. I'm supplying electrical energy and I'm creating thermal energy. So this is how your air conditioner would work. So in your house, you have the AC, right? So this is your house over here, and the AC is set up like this, so that this is the outside, this is the wall, and your AC is connected like this, so that when I turn on the power supply, then the room gets cooled down and the heat which is pulled by the flow of current is dropped in the outside world. So that's how this works. Peltier effect. So let's see if there are any questions. Or shall I go ahead? Because this is maybe I'll just do okay, I can just show you this table. So you can see how these different sensors are used in different ranges. This is something I just pulled online before class. I was just looking for some numbers to put in, and I found this nice table from one of the companies. So I thought it's nice for you to see it. That you can see that for a given what is the operating temperature range? RTD. So you can see RTD has a huge range, right? Supposing I want to use this in a foundry or somewhere like that, where temperatures go to high numbers, like 1750, 650, like melting of metals and all in a furnace, then I definitely cannot use a thermistor. Thermistor itself may get damaged. So then you need to use metallic systems. So that's the advantage of that. Or if you want to, like I told you, if you want to do very low temperature experiments, like I used to do in when I was working in some condensed matter physics experiments, then you had to get very high purity materials like beryllium or something like that, which would measure like very low temperature very accurately. You can see that there are different levels of accuracy, then stability. So you can see for RTD how the stability is very high. That means there is only a fluctuation of 0.05 degrees Celsius per year. Whereas here there is a higher level of fluctuation in thermistor. And thermocouple probably, because you're using multiple metals and all that, it may be more sensitive. I mean, that is, it fluctuates a lot more. And then linearity. So RTD is very linear, whereas thermistor is exponential. So it's difficult to measure. If there is a slight drift, then there is a lot of change in the temperature. So a lot of change in the measurement. So these kind of issues are there. So depending on what is your budget, it always starts with that. How much money do you have? What is the need of your experiment? And then combining those two, you have to choose which is the, based on your operating range and your budget, which one can you take? And what is the requirement? How accurate do you have to be? There is one last set of thing I wanted to discuss, just capacitive sensors. And this is very, very, very straightforward. Okay, there's nothing here. I'm just putting it up here so that you're aware that this is there. So all the things we measured so far are based on light. We measured temperature. Did we do anything else with sensors? So we did light, temperature. I guess that's about it. And then we talked about generation of energy, like LED generates light, Peltier effect generates heat or cooling, the way you want to see it. So capacitive sensor can be used for measuring other properties like say force, displacement. So mechanical effects. We talked about thermal, we talked about light, optical. Here is mechanical. So what happens here is you have a basic, formula of the capacitor is epsilon A by D. You have two plates, parallel plates, which are separated by a distance D and inserted with some dielectric. The area of the plates is A, and this is something you're all extremely familiar with. So the way the capacitive sensor works is I can have one plate which is fixed to some measurement system. So I have subsequent blocks here, which are measuring variables, and one is connected to the actual activity. So I can have some physical medium over here that I'm trying to measure. So it's like a spring or something like that. So I have some force. If there is some force applied on the system, then it will pull the plate up or it will push the plate down. So as you change the distance between the plates, then the effective capacitance changes, right? What is the capacitance now? C is epsilon A by D plus or minus X, right? If I increase the distance between them, it's like D plus X, and otherwise it's D minus X. So it's a simple measurement. So as the capacitance changes, then you know that Q is CV. Q is C times your voltage. And therefore you can see that if it's charged to a certain voltage, then the Q will change. That means there'll be some current flow in the system. Or if Q is fixed, then the overall voltage across the capacitor plates will change. So these are all things that you can experience. Similarly, instead of connecting the medium to the top plate, like I did over here, I can connect it sidewards so that the displacement is sidewards, so that the overlap area between the two plates changes. Okay. So if one plate is fixed, always let's say the bottom is fixed, right? So the bottom is a fixed plate. Here also bottom is fixed. In one case, the upper plate can go up and down. In the other case, it is going left and right. Okay. So as it's moving left and right, the overlap area changes. So the effective area of the capacitor changes, and so the capacitance reduces. So that's one way of measuring the signal. The third case is both the plates are fixed. This is also fixed. but then you have some solid dielectric in between, and the dielectric is connected through a spring to whatever mechanism you have. So as that is moving, the dielectric moves in and out, and the effective capacitance changes. So how does the capacitance change in these two cases? In the second case and third case, what will be the formula? What is the formula for the second case? C is what? Epsilon. D is fixed. So A is changing, and A is changing by some value, A minus W into X, right? Because area is width into X. So I'm changing by X, so W is changing. And similarly, in the third case, the dielectric is changing. So in one case, there is a fixed dielectric.
2x.
2x. Why? Yeah, 2x. Good. Minus 2wx. Okay. Then in the third case, what happens? It's epsilon 1 and epsilon 2 are changing. So there it's epsilon 1 into wx plus epsilon 2 into a minus wx by d, right? I don't know, you're the IIT guys, so you probably know all these things quickly. So if C changes, how can you measure the signal? That's what I wrote over here. If the capacitance changes, then you know this relationship changes, Q is equal to CV. So if I have a fixed voltage, then as the capacitance changes, some current will flow because Q will change. So I can see some instantaneous flow of current. Or if the Q is fixed, then I can see a change in the voltage. Yeah, supposing it has constant charge, then by multimeter you can measure potential. Normally what happens is you cannot use a multimeter for this. The multimeter instruments are very coarse. They cannot measure such fine changes. And multimeter usually does not measure transients. It measures only DC values, the multimeter we have in the lab. So these might require more sophisticated ways of having measurement circuits. In fact, instead of multimeter, you may have to put some BJT kind of thing, do some transient response, or use a peak detector circuit so that it captures the peak of the change. You have to be a little innovative about it. And finally, the last thing is you can also have a capacitive humidity sensor. In one case, I said you can move the dielectric in and out. But in this case, what's happening is the dielectric constant itself is changing. So I have two plates. The glass substrate is nothing, it's just a substrate. Then I have one metal which is tantalum and another metal called chromium. These are two plates of the capacitor, and in the middle I have a polymer dielectric. So when I want to have a humidity sensor, then the humidity will, the water molecules will interact with the polymer dielectric and change its dielectric constant. And because the dielectric constant changes, then the overall capacitance changes and the voltage changes. So this is actually not a force transducer. This is more like a chemical transducer. It's by the purpose of chemical energy. It's changing the chemical energy of the dielectric material, and that is getting converted to electrical energy. So these are all various types of transducers. And very interesting. It's a lot of fun stuff. You have the time to do all this. So now maybe I can take any questions. Yeah, there is a lot of overlap in use of materials and science because a lot of modern technology is actually being driven by material science. A lot of the theory that was developed in the past is being modified as the materials are changing. Same thing is happening with all the diodes and all this. Even the very fundamental questions we ask about the common emitter characteristics, what is the value of beta, why does the op amp have infinite impedance? All of these were valid at a certain time period when there were a certain kind of materials available. As things are changing, a lot of these fundamental definitions are also changing. Can you explain humidity capacitance? Well, all we are saying is capacitance is, we said the basic formula of capacitance is epsilon A by D, as shown over here. And when there is humidity, then the water is interacting with the dielectric material. And due to interaction with dielectric material, epsilon changes. And when humidity reduces, then the dielectric material gives up the water. And so again, its epsilon changes. So you just characterize it by changing the chemistry of the material. Why was it 2wx? Because as pointed out by one student correctly, if I'm shifting it by x over here, I'm also losing x over here. So there is x here and x here. Both are happening simultaneously. It becomes 2x. Is that correct? I don't know.
Sir, it's 1 Wx. So we take area for one plate.
Yeah. Okay, let me see. So this is originally this was the area of overlap, and now it is changed by x. Yeah, so I confused myself. It should be Wx only. So it's correct. Okay. So that's capacitor, temperature. So that's about it. So I think next time I'll talk about some more things, like still with semiconductors, I'll talk about Hall effect, how you can use, or maybe I may just put a video recording for tomorrow. And because I've already done this last time, and I can put let me stop the recording.